A little bit of housekeeping before we start. We will need these a lot. So these are sticky notes, and the sticky notes come in two colors. This color, which I will randomly call yellow, orange, red, or pink. Not yellow. You see, I'm already confused. Red or orange or pink, depending on the supplier we have when we teach, we have different colors. Or this one, which I might call green or yellow. Okay. And sometimes I will call these green and these red, but I'm sure you will correct me. So we will need these a lot. And how are we going to use these? We are going to use these as an aid for interaction, to promote interactivity, and also as an aid for me to get an idea of how well it goes. For example, when you do your exercises. So, first rule of good teaching is interaction. So we are going to try to make this course as entertaining as possible, and we're going to make everything we can so that at the end of today, at the end of tomorrow, and at the end of the Friday, you leave this room being happy with yourself that you have learned something. But for this to be possible, we need it to be as interactive as possible. So, please do not hesitate to interrupt me at any point in time. But sometimes some people feel a little bit uncomfortable by, I don't know, raising their hand or stopping somebody when they talk, and that's perfectly fine. So that's why we also have these. So if at any point during an exercise when I talk and you don't think it's the right time to raise your hand and interrupt me, which would be perfectly fine, I'll repeat it multiple times. So what I would ask you to do is to take this color, kind of the orange, and put it like that on top of your screen. Yeah. That will allow me to see there is somebody that has a question, and actually that might even allow me to see that multiple people have a question, which very likely will be the same or similar question, which means I haven't done my job well. Okay? So by asking questions, you'll help me to improve my teaching, and you'll help everybody to improve your learning. So we will also be using the sticky notes during the exercises. So we'll start an exercise, and then if there are some sticky notes that are still up, I'll ask you to bring them down. And then during the exercise, if there is a question, if there is a problem, again, you're happy to call us, or you just use your orange sticky note and put it like that again, so that we can see that there is a problem and we can come and help you. If you have finished the exercise, or you just had enough of the exercise, you're happy for us to proceed, whether you have finished or not, then you take the green sticky note and put it like this on your screen. So again, as instructors, we can then see how you progress. We might not wait until we have 100% of the green sticky notes up, because some people don't like to use sticky notes, so they don't use them. That's fine. But at least we can get an idea. Do we have 10% of the people that have finished the exercise, or do we have 90% of the people? Okay. So that helps us to make sure that we pace the teaching in a way that is as helpful as possible for you. Good. So please, could you take one of each and then pass them around for you? Oh, in addition to the high-tech sticky notes, we also have low-tech USB pads, USB drives. These, so I'll pass these around too. Could you take one to your neighbor? So these USB drives contain the material that we will use during these 3 days. Okay. Oh yes, I have been told that at the end, is it today or at the end of Friday, sometime, if you could return, you can keep the sticky notes. If you could return the USB drives, whenever you have copied all the files locally. Good. So, here is the content of this USB drive. So we have 3 HTML files that contain the material for day 1, day 2, day 3. We have this readme.html file that I'm going to show in a minute. A directory here, installation. These are the instructions that you got by email a week or so ago, and some data that we'll be using throughout the days. So I'm going to start by double-clicking on this readme.html file. So in addition to be available offline, all the material is also available online. And so if you click on this link here, it will bring you to this GitHub repository that Olga mentioned, where all the material, including the slides she showed, are available. So I know some people have issues with the wireless, but you have all the material on your USB drives. Ah, good. Okay, the technology hasn't failed yet. Thank you, keeping me on my toes. So the material is also there online, and what I will do is throughout the day we have some exercises. We'll check all the exercises together, but what I'll also do is that I will update this material online to add the exercises. Okay. So from this file that you have locally, the first link here brings you to the online material that will change a little bit throughout the 3 days, where you will have all the answers. So there is a second link here that opens an Etherpad. An Etherpad is a notepad, a very simple text editor that we can all use and edit collaboratively. So it's the second link here. So, for example, you can get a little color next to your name. And for example, if I start to edit here, let me add. Okay, so this is my Twitter handle. So we can all edit this document collaboratively. Sometimes when I teach, people like this a lot, and they edit it a lot. And sometimes people, or maybe it's me, they don't find it useful and they don't use it. So we will see how it goes. However, I have set it up here. So if you want, for example, you could add your name here and the contact detail if you want, so that we have an idea of who's here. But the reason I have set up this Etherpad is that throughout the days, we will have questions that you can ask and we will answer immediately. But you might have slightly bigger questions. And in that case, that maybe is not the right time to address immediately. So in that case, if you have bigger questions that you would also like to discuss at the very end of the sessions or at the very beginning at 8 o'clock in the morning, where you can bring your own data, please write your questions here so we have a record of all the questions that people are interested in. And these are kind of discussion topics that we can then focus on later on. Okay? For those that have issues going online, so if you have a question and you can't update the Etherpad, could you just take a sticky note and write your questions here? And so at the end of the day, just leave it on this table, and then I'll collect the questions and update the Etherpad accordingly. Oh, question.
These links are on GitHub? Is that, how do you get here?
So, so if you open the HTML, readme.html, here are the links. Okay. The first link actually opens this page, but on GitHub. The second link opens the Etherpad. Okay.
Sorry, which one was that?
readme.html. The last one. Okay, so let's use the sticky notes. Could you put a green sticky note up if you have got a USB drive and if you have copied the files locally, otherwise the other color. Quick clarification, we do not need to have access to GitHub. Okay? I just tell you, but we have everything on the USB drives. Okay, very good. Unless there is another question, sticky notes down, please. All right, very good. So let's start with the first material, which is the 01 here. Okay. So I'll not systematically show all the material and go through it. I'll try to make sure I don't forget anything. I might say a few things that are not in the notes, but all the kind of official material is here. Okay, so you can open it, and here's the material. And so the objectives for this first afternoon really is to tame the beast. You know, R. I assume you have all heard of R. Yes? Have you used R? Who has used R here in this room? Okay, so quite a few people. And by the way, there are no prerequisites expected. Okay, so it's perfectly fine to say, I have no clue what you're talking about. I have never programmed. That's fine. Okay, so you have heard about R. So the idea for this afternoon is to get started with R and R Studio to familiarize ourselves with it. And so tomorrow, we'll get started with slightly bigger data, real data, actually data from the design that Olga has introduced earlier, and to visualization, exploration of the data, and do some basic statistics, and then third day, hypothesis testing, correlation, and things like that. So there is the material, but what we want really is to make sure that whatever we cover, you learn, you master. There is no reason to hurry through the material to absolutely get to the end, okay? So just like making sure that everybody follows, that is what matters. There is no reason for us not to get to the end, but that's not the priority. So let me show you how R looks like. And this is not how we are going to use it. But this is R that is open, kind of naked. Naked R looks like this, and it just waits for us to type things. So R really is two things. It's this environment here that waits us to type, interactive environment, and R is also a programming language that we can use to write software, just as you would do in Python, C, or other languages. But really, it's a continuum between using R interactively for data analysis and programming. So of course, we are not aiming here to learn programming and write software at the end. That's not the point. We'll start with data analysis, mostly using it interactively and writing script. But hopefully, towards the end of this course, you'll see that actually data analysis is programming. It's programming data. It's not writing software, but it's programming data. So R is these different things, starting from purely interactive to full programmatic. One thing you will have noted is that R is not a graphical user interface that you use with your mouse to point and click. So the way we will interact with R is by typing on the keyboard, which sometimes feels a bit odd, but this has many advantages. And one major advantage is that whatever we type in the keyboard, so using the keyboard, we can type in a file and store and save that file. And this is a very accurate record of everything we have done. So we don't need to remember all the clicking actions that we did. If we want to repeat what we do today, if we want to repeat it tomorrow, next week, or in a year, everything, we can record everything in a file and then reload that file and repeat, copy and paste. We're not going to copy and paste, but rerun all these lines tomorrow, in a week, in a year, okay, to exactly repeat what we did. So although this command line interface might feel a little bit alien at first, it is a fantastic tool for reproducible research. Okay. So that's one of the kind of concepts that we will explore a little bit more later on. Reproducibility and reproducible research, especially at the end of today. R, as such, as it here, is actually a pretty limited piece of software. It does basic statistics. It does, I'll say, decent plotting. One of R's strength is plotting. It's very good. But actually, tomorrow we will see more advanced plotting that we get here with kind of the base R. So, although R is great, on its own, R is limited to basic statistics, basic plotting, and some other functionality. But one of the strengths of R is that it's relatively easy to extend R by writing packages, kind of modules that give extra functionality to R. So if you want to do a microarray or high throughput sequencing or proteomics data analysis in R, and you only use base R, you'll have a lot of work to do. But thanks to these packages, there are thousands and thousands of statisticians, computer scientists, biologists that have contributed their expertise to R, provided some packages so that today we can use, well, no, we don't do it today, but we can now use R to do many, many different tasks. And so R is used in life sciences, in academia, but in banking, in industry. So R is really used across the range thanks to these tens of thousands of packages that are there. And with this kind of many packages, there is also a huge community around R. And the last point that I noted here, and I don't know to what extent is this something that's important to you, but R is free, but not free, or not only free as you don't need to pay for it, but free as in open source. So there are many people that look at these, at R itself, look at these packages and provide a kind of fully open, collaboratively developed ecosystem for many types of analysis. So this is kind of naked R, but that's not what we are going to use. Well, not only. So let me close this. What we are going to use is another piece of software called RStudio. And so on this computer, well, the icon is always the same one. It's kind of a blue sphere with a white R in. And that is what we're going to use to interact with R. Okay. So, could everybody please open RStudio and put their green sticky note on their screen if RStudio is up and running? Okay, that's close to 100%. Very good. So here's how RStudio looks like. And I'm just going to open here like this. So we have 4 panes. RStudio is composed of kind of 4 different bits. The one here at the bottom is actually exactly the same thing that I had before. This is actually R running here within RStudio. That's called the R console. And the greater than sign here is R waiting for us to do something. Okay, so for example, if I type 1 plus 1, it tells the result, which is 2. This is actually R. Here at the top pane, we have an editor that allows me to write some code without executing it in R. So here is a really great place where I can start to write all the commands that I want R to execute and store them. That would be one first step for reproducible research. Here is a pane that, among other things, shows us a set of directories and files that we can navigate. Here is also where the figures will appear and where the manual pages will appear. And here at the top, we can see all the variables. We'll see what it means. And all the things that we create in R will appear here at the top. So I suggest that to get started, we are going to create a directory for these kind of 2.5 days. And that's my suggestion. You'll do whatever you want, but my suggestion would be to say that in this directory, we'll try to write the scripts to save the figures of everything that we're going to do during these kind of 2.5 days. And actually, these directories and files, we're going to create them through something that is called an R project. So if I open here, File, and I create a new project by selecting New Project. So this new project, I want it to be in a new directory, and we'll create an empty project. So there are different types of projects, but we, in this course, we'll only concentrate on the empty project. And so it asks two things. The first one is the kind of name of the directory for my project, and my suggestion here would be just to call it rstats. Feel free to call it whatever you want. And the second piece of information is, where do I want to create this project directory? And here I will create it on my desktop. Again, feel free to create these wherever you want. Open, and then create project. And now, in my files panel here, RStudio automatically opened this rstats project directory and automatically created a file called rstats.rproj that kind of encapsulates some metadata, some information about my project. Okay? Once you have created your project, could you please put your green sticky note up? Okay. Now, some kind of good practice is, in the frame of a project, is to try to create some compartments for different types of data. Okay. So first compartment that I would suggest that we create is a new folder. So we can click on the new folder icon here, and we create a new folder or directory called data. That will automatically be created inside this R project directory. And a second piece of information that I think we could already create now is a script, okay, a file that will contain R code. So to do this, to create this file, we click on RStudio module, not RStudio, file, menu, new file, and the type of file that we want to create is an R script. And so this will open this panel here at the top, in case it was not open yet. And let's save that file. And I'll call it rstats stats01. Save. And it will automatically create or store that file inside my rstat project directory. Okay, so once you have created this data subdirectory, oh, and one more thing is that now what I would like you to do is So in the drive that you got, there is this data directory with all these files, 2 CSV files and 2 RDA files, and we'll see what these are later on. If you could take all these files and copy them into the data directory within your R project. And once you have done that, could you put your green sticky notes up? Yes. So here is the directory that was on your USB drive. On that USB drive, there was a directory, what was it called? May Institute P3 Introstat. In there is a directory called data. These are some data files that we're going to use throughout the 3 days, 2.5 days. So could you copy these files in the data directory and move them into the data directory of your R project? I called it rstats. And in the meantime, I'm going to change this. Okay. And while you did this, what I did is I changed the layout. Sorry, is there a question?
Exactly what you're saying right now. We want to know what happened to the
Okay. So while you did this, what I did is that I changed my panels here. And I changed them so that on one side I have my R script, and the other side I have my console. Because if I start typing things in a panel at the bottom, people that sit there at the front, I type something here, people will not see it. And if I type something here at the bottom, somebody else might not see it. So I will concentrate on my console panel and my R script panel. And I want to maximize that space so that you can see it. You do whatever you prefer in your case. The reason I do it here is for teaching so that everybody sees. Sometimes other panels will open whenever they need to pop up. They will open, and then we'll kind of look at them. But now I prefer this setup for teaching. And a last quick comment before we proceed. So if this is your kind of project directory, what we did is that we created a data directory to put our data, but there is only your imagination that can limit the way you can structure this R project directory. And the way you will structure it will depend on how you want to work. Okay? It's how you're going to structure that work, how you're going to structure that project. So many people, for example, have a data output directory, where this would be the data that we use as input, and once we create new data, we'll do that throughout days, they would store this new data into another data directory. As you prefer, you can keep the same ones or 2 different ones. We will create many figures, so once we create figures in RStudio, they will show up here, but if we want to write them to a file, we could save them in a figure directory or fig output. We put our script within our main directory, but we could have a scripts directory and put them there. So this will very much depend on your project. My suggestion for today is to keep, oops, sorry, wrong button. I will embarrass myself throughout these 3 days because it's pretty much the first time I use a Mac. Oh yeah, that's not what I wanted to show you. Here. Okay, so I think for these days, something like this with the data and scripts here is probably enough, but you will have to adapt this depending on your projects today, tomorrow, and later on, because I really hope you'll carry on using R. Okay, and so here now, if I click on my data directory, here are the 4 files that I copied over from my USB drive. Okay, are we all fine with that? Is there a question? Can I help you? Yeah. Oh, okay. If, you can come later, and we can follow up. Good. So, so one very important thing that we all need to know when we use R, or when we learn R, is how to find help. Okay. So now, the easiest way probably to find help is to ask us. But R comes with a huge amount of documentation that comes with R. And some of the exercise will require from you to read the documentation or open it up. And to do that, in your console, you'll always use the question mark. The question mark means, help me about a specific topic. And for example, if I want to get information about the piece of functionality to calculate a mean, I would type question mark mean, enter, and that would automatically open in this panel here the documentation for the mean function. So, as for every good piece of documentation, rigorous technical documentation, the first time we read it, we do not understand. And it is perfectly normal. That's the point of the documentation. It's written by experts for experts. But very quickly, you'll get used to it, because these documentation files always come with a specific structure. Okay, they always have a title, they always have a description, and then for functions, they always come with kind of these sections that tell you what kind of things can you use when you use this functionality. Okay. And probably the most important section in these documentation files are the examples here at the bottom. Okay. So whenever I hit the documentation of a function that I don't know, I quickly scan over it, and then I hardly understand what they really mean. So I go at the examples and I try to run them, and just to see, what does it really do what I think it's supposed to. So, very important section is the examples in the documentation. And once you get a kind of a feeling of what's supposed to happen, then you can come back to the actual documentation and read. And believe me, after a little bit of practice, these documentation files will prove very, very useful. But yes, the first time, they are very technical. So that's what happens if we type one question mark, okay, when we know what we are looking for. But sometimes we have a vague idea that we are looking for a concept, not a very specific keyword, not a specific programming word that we know exists. And in that case, we can use two question mark. Okay, and press enter. And then I probably there we go. No. Okay. So if I type two question marks with mean, this means look for this keyword in all the documentation files that are currently installed. Okay. And this allows me to kind of navigate through the documentation, even if I don't know exactly what I'm looking for. And let me just kind of open one at random. No, this one is not very useful. Okay, so back to my documentation of my mean function. Another helpful section is the see also section. Okay? So if I know I'm looking for a mean, I can start by kind of navigating R in the mean manual, and then kind of see, oh, I have a mean, but I have a mean for that kind of data. I can calculate means for columns, matrices, for example, and I can calculate a weighted mean. So documentation is also a really good way to learn more about R, about new functions, what can be done. So if you have a little bit of time, you can just open R and start with documentation, one documentation after the other, and then you'll learn many things. So there are also, there is a lot of help available online. There's tons of documentation available. So for example, if we type help.start here, this opens this page with links to an introduction to R, which would be kind of a general basic introduction to R. These two, which are writing R extension, which would be more advanced, and again, that's the kind of documentation the first time you read it, you understand it. But there is a lot out there about R. On the R web page, just kind of browsing internet, that can help you to find a lot of documentation if you want to learn more. There is also an R mailing list that you can ask questions to. If you know the Stack Overflow website, which is a site where you can ask questions about any programming language, well, they have a specific tag for R. And the community is generally really good to answer your questions very, very quickly. But asking a good question is not always easy. And actually, when I have questions myself, I will try really hard to define exactly what my question is, to really understand my problem. And by the point I know, now I can write a question that really describes my problem. If I have a script of 200 lines of code, I'm not just going to say, oh, here's my script, fix it for me. No, I'll try to find exactly where is it that it fails. By the time that I do that, very often I understand what was the problem, because I can work through the problem and that I'm in a position to fix it. So asking questions is actually something really, really difficult. And again, takes practice. And the better question you ask, the more likely it is that somebody will answer it very, very quickly and help you. And so there is the R mailing list and Stack Overflow, really precious resources. And there is a link in the documentation about making sure that when you ask questions, try to ask them in a way that helps people to reproduce your errors. If I just send an email and say, this bloody thing doesn't work, help me, nobody's going to help me because I haven't described my error and they can't reproduce it. So again, there is a link in the documentation file that gives some advice. And one piece of advice is to always provide some information about your working R environment. Oh, there is a question there? Yes? Very good. Well, thank you very much for asking this question. So my suggestion would be to use this R file here that we have. So that would be the best place to write R code. So for example, if you'd say, this is some piece of R code that helps me to open the documentation file. And so if I write valid R code in here, if I write some valid R code in here, or for example, 1 + 1 is something that we had, we need an easy way to say, here's some R code that I wrote, and here's where I actually need to kind of copy and paste the R code so that it gets executed. And you can do that by moving your cursor on that specific line and then press Control-Enter. And that will kind of automatically take that line of code and inject it in the console. I could also select and type run, click run instead of typing Control Enter. And if I press source here, let me here write 10, 1 plus 10. I'm just going to remove this for a second. If I click source, it will automatically execute all lines, the whole file that I have here. Okay. We don't see this appearing here, and we'll see in the second one. Okay. So whenever you want to take notes about R code, there are two places where you can write your R code. In the console here, and that's very nice when we play and we try, but as soon as we write something that we think is very important, then it's much better to write it in your R script, so there is a record. We are not going to lose it. But you probably don't want to write R code and only R code as notes. So when I write software, I do not only write code, I also write kind of general information comments. Okay, this should be two. Okay. Now the problem is that this is not R code, and this editor here tells me there is a problem here. You see the little red label tells me that this is a problem because it's not valid R code. So what we can do is to write our general notes as comments. So if I start my line with one or multiple, I always forget the name of this character in English, dash, hash. Okay, one or multiple hashtags. This means what follows just should be ignored, whether it's R code or whether it's not R code. So that would be a way to take your notes. And at the end of today, we'll see another way, but that would be kind of, I think, a good way. So I was saying, when we ask questions, one piece of information that is very important to share is what version of R do we use? What version of packages are we using? And to do that, and I'm going to type in here. To do that, there is a function. A function is a kind of computational object, just like a mathematical object that does something. It can take an input, it might not, and it returns an output. And you can always recognize a function because it has parentheses. Okay? So we're going to use the function session info with a capital I. So R is case sensitive. Session info like this is correct. Session info with a lowercase I or capital S is not correct. R will complain. Well, let's try. Let's see what happens. Session info like this, Control Enter. And R complains. And we know R complains because they use the dreaded error. Okay? And there will be many errors. You will get errors. I will get errors. I got over it because I got so many errors that now I just accept it. But it's in red here, and we have an error. And very often, these error messages are hard to understand. You will not get immediately why is R complaining. Okay? So again, this takes a little bit of practice. And because we will get many errors, and I will write errors here in front of you, so we'll learn how to decode this. But here it says, could not find function session. And it knows it's supposed to look for a function because we have these parentheses here, and it says that it just couldn't find it. So whenever that happens, we need to identify what's the last line that I tried to run. In this case, it was a typing error, Control Enter, and in this case, no error. That means it's successful. And this is the output of session info. The session information tells me what version of R am I using, what platform, OS X, Linux, Windows. And this is actually quite important. It will tell me what are all these packages, these extra add-ons that are being used at the moment. So whenever you have a question, make sure you provide the output of session info so that people are in a better state to help you. Let me remove this. So we have seen that we can use R as a giant calculator, which is not terribly useful. So we need a way to store all these results. So if I type 1 plus 1 here, now let's imagine it's not 1 plus 1, but it's the output of a really important calculation that R does for us. At this stage, the only thing that happened is that the result of this calculation is displayed here in the console, which is not useful. Of course, we could write it down on our sticky notes, but it's kind of lost. So we need a way to store these results inside R. And the way we do it is by creating variables. So for example, naming variables is a very difficult topic among programmers. There are good ways and bad ways to name variables. Most of the time, I'm going to use bad ways because they're shorter to type. So I'm going to have a variable called x. We have no idea what x means. Is it something useful? Is it something not? So maybe I'll do an effort now, and I will call something weight. What's the example? Yes, kilogram. So I want to store some piece of information, and this piece of information is weight in kilogram units. And so this is the name of the drawer, if you want. I'm going to store something in a drawer, and on that drawer, I take a label, a sticky note, I write weight in kilogram, and I paste it on my drawer. Okay. And so now I have this drawer where I can put some information, and the way I'm going to put information, wrong keys. Okay. Is with this left arrow, which actually are 2 characters, a small than sign and the minus. So here we go. So this means assign the value 55 to my variable weight in kilograms. This really is the computer having a drawer, writing weight in kilograms, taking 55 and put it in and closing the drawer. The only thing is that it's not a drawer, it's an address space in memory, but that's exactly what happens. Assign value 55 to weight in kilograms. And so if I execute this line of code, nothing happens. Actually, that's not entirely true. Depending on how your RStudio is configured, you'll have something that has appeared here in your global environment. And that is to tell you that you created a new variable, weight in kilograms, and to that name, that variable, you assigned it value 55. And now we can always recover this value 55 by typing the name of that variable on the console. And you might already have realized that once I start typing in RStudio, and that's something that's not working with base R, it starts by suggesting R keywords that R knows about that start with WEI. And then I can use the tab key to autocomplete, and this saves me a lot of typing. So even if we are not very familiar with the keyboard thing, RStudio will help us to kind of minimize the amount of typing and the amount of timings. And so by just saying weight, kilogram, enter, I can access the value that is stored in that variable. Which actually is exactly the same as saying print weight in kilograms. So print me the content of that variable. Instead of writing print, I could just type the name of the variable and it would be displayed. Okay. So let's try to do this and 110. And I'm going to write this, execute this other line of code. I start by executing this one, and now I execute that one. What do you think has happened? You'll probably, if you do it, you'll probably see it, in your pane, in the kind of environment panel. The variable is still there. The drawer is still there with the same label, but the content in the drawer has changed. And how can we check that? Oh, another really useful keyboard shortcut is the up and down arrows. So if I want to go back in history of everything I typed, I use the up arrow until I have print, wait, or just wait, enter. So here I create a new variable with value 55, and here I update the content of 55. And so if I somehow mistype, okay, I press enter, I get another error. Object, before we had function session info not found. In this case, it doesn't expect a function because there is no parentheses, but so it just says kind of object, which is much more general, weight kilogram not found. Okay, and what do you think is going to happen if I type? And the shortcut for the assignment, kind of the left arrow, is Alt minus. Alt minus is kind of a shortcut to automatically create that key. So what do you think is going to happen if I type this? Okay, and I execute this? What will be the content of my weight kilogram variable or draw after executing this line? Anyone? Sorry, I'm not very good with hearing, so you... 220. Let's see. I execute it. I move back to my console. And actually, there are shortcuts for that. Control 1 moves to my script. Control 2 moves to my console. Okay, Control 1, Control 2. I up arrow to go back in history. Enter. Oh, an error. I told you, many errors. So I need to go a little bit further back. Enter. And another error. Here we go. 220. Exactly. So this line of code here actually does two things. It knows that at some point it will have to update the content of my weight kilogram. But before doing the assignment, R is going to look at what's happening on the right-hand side of my assignment arrow. So what does it need to do? It needs to do a multiplication. What multiplication? Weight kilogram times 2. What is weight kilogram? Okay, let's go check in our drawer, extract the value, and then multiply it by 2. And this new result is going to replace the old value of my variable. Okay, so this kind of mental exercise of impersonating R, how is R thinking, is something that is very difficult at the beginning, but throughout these days, it will become much easier. That line of code, you don't need to know the result. Right? That's why we use R, to do the hard maths, to do the stats, to do the computation. That's why we use computers. But what we need to know is that when we look at this line of code here, we need to mentally understand what is going to happen. So one thing that could happen is an error. If there is no weight underscore kilogram, if there is no such variable, there will be an error because R will try to fetch a value from this variable it won't see it. Assuming this variable exists, it's going to take the content of it, multiply it by 2, and then replace the content of this variable. So that's the kind of mental exercise that we need to know and familiarize ourselves with the R syntax. That is actually something very, very important, especially later on when we will write much longer expressions. And actually I learned that the importance of reading code and kind of mentally parsing the code when my children started to read. So the way it is in the UK is that they don't start with letters, but they try to identify phonemes, so groups of letters that they can pronounce, like cat, cat, or And then they put these together to make a word, cat. And that's exactly the kind of things that we need to do to start and familiarize ourselves with reading code. When we see this expression here, this command, we need to see that, first of all, we can split it in two based on the assignment operator. Okay. On the left-hand side is what's going to happen at the very end. First, we have to concentrate on the right-hand side. That is where the action happens first. And the result of this action is going to be used to update what we have on the left-hand side of the assignment. Okay. So what do we have on the right-hand side of the assignment? A multiplication. So again, multiplication, we split it in two. On the left-hand side of our multiplication operator and on the right-hand side of the multiplication operator. Here, 2. There is nothing else to do. 2 is 2. But on the left-hand side, we have a variable. So first, we need to go and get the content of that variable, do the multiplication and assign. So that is something that will feel quite difficult in the beginning. Seeing this code, and it just looks like gibberish. But I'm pretty sure that by the end of tomorrow, you'll familiarize with yourself. And we will end up writing pretty long lines of code. Okay. Go. So here's the first exercise for you. Is it? Yeah. Here it is. And how can I increase the size of this? Shift plus, Control plus. Here we go. Here's the first exercise for you. Look at these expressions. So these are valid R expressions. And can you identify what the value of these variables are after executing all these lines of code? Okay. Have a look at it, or just try it out as you prefer. Okay. So once you have figured out what the content of these variables is after each row, after each command, please put your green sticky notes on. Oops. Just going to paste the questions here. I see many sticky notes, green sticky notes here on the right-hand side, not enough on the left-hand side to assume that we can proceed. So anyone, what's the value of variable mass after executing that line of code? After executing the first line of code, what's the content of Well, so when we execute the first line of code, so number 1 there, what's the value inside mass? Thank you. Second line of code, what's the value in mass? Good. What's the value in H after running the second line of code? Yes. What's the value in mass after executing the third line of code? Whatever it was before multiplied by 2. I'm not good with calculations, you know. I'll add that to R. Okay. What's the value in H after executing the fourth line of code? Whatever before minus 20, exactly. And the last line of code? I'll trust you. I don't know. Whatever there was in mass divided by whatever there was in H. Okay, so these are variables, kind of drawers that store values. But there is another, and we have briefly seen them, functions. Okay. Functions, just like in maths, are operators. They do something with an input. So if we look, and we can identify them with parentheses. So if we take, okay, the round function, and we provided this value as input and press enter, it's going to round it. Okay? And default rounding is like this. But actually, if we look at the documentation of round, so question mark round, we see here that round takes 2 inputs. This is the name of my function, parentheses. The first input is called x. The second input is called digits. And the default value for digits is 0. So whatever the first input is will be rounded with 0 digits behind the dot. So what if we run round with digits equals to 3.14. So this is a function, it takes 0, 1, 2, or many inputs, and it returns a result by taking these inputs, doing the computation, and returning it. So instead of naming our inputs, digits equals 2, we can just rely on the order. Okay. The first input is x, the second input is digits. So we don't need to specify it here. That's if we know the round function. If we know it well enough, we don't need to specify. If we are not sure, we check the documentation and we spell out the name of the arguments specifically. So what happens if I tried to type this? What is round going to try to do based on the documentation? This doesn't make sense. We can try. Okay. So there are always many things that happen behind the scene. Okay. So R knows that this needs to be an integer and probably rounds it, and 2.00, remains 2. However, if what we meant really is to say digits equals and x equals, then we can change the order as long as we provide the names. Now, this is very confusing. It's very dangerous to try to play around with the order of the names. It's very confusing for somebody that, we always expect x is the first input, digits is the second one. But this is to show you that if the inputs are named, or arguments, the arguments are named, that's fine. They're going to be matched by name. If they are not named, then they're going to be matched by position. Functions. They take an input, matched by position or by name, they do the calculation, and then return a value. Let me execute these. Source. So nobody asked what this number 1 here was. And so what we have created so far in these variables are vectors. Vectors of length 1. So they only store one piece of information. But actually vectors are much more general, and they can store any number of items that we want. So let me create another variable, another vector for peptide length. And I'm going to take the same example as I have in the notes. Sorry, I forget half of my. So assignment operator, I either update that variable if it already existed, or I create a new one. And what I'm going to do here, okay, what can you identify in this piece of code? Anyone? There is something that we just talked about that is there. It has a very short name. What is it? So what's new in this? Something that we haven't seen yet. C. What is C? Yes, thank you. Okay. What's just behind C? Parentheses. So that means that C is a letter. Yes, but in R speak, it's a function. So even if you have never seen C, but you have learned about functions, that's part of this parsing R code. We see a parentheses. So even if we don't know whatever this is, we know it's a function. Okay? And we know that within the parentheses, these are the inputs to that function. That function is going to take the inputs, return a value, and store it inside this new variable. So let's type this new variable and see what it gives us. 17, 13, 7. So C is a function that takes all its inputs. The inputs are separated by comma and concatenates them. So mass is a variable called a vector that stores a single number. Pep length is a variable, also a vector, but a vector that stores 3 values, 17, 13, and 7. They are together. They have a position. First position is 17, second position is 13, third position is 7. And actually, we can learn about the new function called length that takes an input and returns the length of that variable. Okay. So what would be the length of mass? 1. So I'm just going to cheat a little bit and do some copy and pasting if I manage to scroll down. So let's create a new variable here called peps for peptides. So here are 3 peptide sequences. And here there is one fundamental difference between peps and pep length. Well, pardon? Quotation marks, exactly. And what does that mean? Yes, strings. In R we call them characters. So these are strings and these are numbers. So there is something that these 2 vectors, peps and pep length, have in common. What is this? What do they have in common? We created them with C, exactly. Both have length 3. Both are vectors. This one is a vector of characters. That one is a vector of numbers, of numerics. And one way to find out what kind of variables these are is by typing class. Class peps it's a character, class pep length. It's a numeric. And actually what we are doing now, it looks very basic, it looks very simple, but we are doing the first steps of data exploration. Tomorrow, we are going to do very similar things on this IPRG dataset that Olga introduced. So now we are practicing on small data, on vectors of length 3, 5, it doesn't matter. But the same principles, what is this thing that I have here? I have this variable. I don't know. Is it a huge data set? Is it a small data set? R doesn't really care whether we have a vector of length 1 million or a vector of length 2. If we ask for the length of it, it will return 2 or 1 million. But we do care. And so we need to learn these tools to explore the data. We try this on simple vectors now. Tomorrow, we'll do the same type of exploration and more kind of involved exploration to understand our data sets. And that's how the data analysis starts. It's not with a statistical analysis. The analysis starts by looking at the data and kind of making sure it fits, it matches our expectations. Another very useful function is str. Str stands for structure. Structure tells us CHR, it's a character 1, 2, 3, 1, column 3 means it has elements 1, 2, 3. Let's try to type 1, column 3. 1, column 3 means create a sequence 1, 2, 3. Okay. 1, column 100 means create a sequence 1, 2, 3, 4, 5, 1 to 100. Okay. So this is a character of length 3, and here are the first few values. And now here we see what this 1 here that we had at the beginning means. This is actually the index of the first element on this row. So this is 1, 2, 3. What's the last one? That's actually 13. Of course, it's 13 because they have numbers. Okay, so 14. And we do it with letters. Letters is another variable that contains the lowercase letters of the alphabet. And n is the 14th letter. Okay, so these are the indices. So we have created a vector. Peplen. Okay. So if I want to add a value at the very beginning of Peplen, I can use C, and let's say I want to add, 5. This concatenates 5. 5 is just a vector of numbers of length 1. And then to this, it concatenates the content of this other variable. If I want to add, let's say, 10 at the end, I would concatenate this vector of numbers with another vector of number that is just 10. If I wanted to add 5 at the beginning and 10 at the end, this is how I can kind of modify, manipulate, increase the size of my variables. So we have seen numbers, we have seen characters, we also have logicals, true or false, complex numbers or raw values. During these 2.5 days, we'll concentrate mainly on numbers and characters and logicals. And we will introduce them slowly. So, another quick exercise for you. Oops, here's my exercise. Here. So what we have done so far is that we only saw vectors of numbers or vectors of characters. So what's going to happen if we start to concatenate numbers and characters? So could you try to run this first line of code here, where we use the concatenation function? It's a function, so we need parentheses, 1, 2, 3, and A. Now whether you have single or double quotes doesn't matter. And we create a num underscore call. What is this num underscore call? Is it a mix of numbers and characters? Is it a number? Is it a character? You tell me.
It looks like it's all characters.
It's all characters. How did you find out?
Because they're all with the quotation marks.
Yes. So, from this we learned two things. The first one is that vectors can only contain elements of the same type. It's either a vector of numbers or a vector of characters. This also means that when we mix numbers and characters, the numbers will automatically be converted into characters. Why is that? A character can't be a number. Okay, and so what if I have this? So this is a character, but I could somehow convert it to a number. But this one would be much more difficult to convert to a number. We could find convoluted ways, but right. But however, any number can always be converted to a character. We just need to quote it. Okay? So there is a concept of a very general type and a much more specific type. Numbers are very specific. Characters are very general. We can take anything and convert them to characters. Okay? So here's another example where we concatenate numbers 1, 2, 3 and the logical true. True all in uppercases. And converse of true is false all in uppercases. So what happens if we concatenate numbers and logicals? What do we get? So here, this logical was converted to a number. Let's see what happens if we say false. I don't need to store it in variable. I'll just execute it here interactively. Okay. False was converted to a 0. So this is called coercion. So, things sometimes happen behind the scenes. So we think we have a type, and then they might get converted to something else. So this is, again, very important why we need good data exploration. We need to make sure that what we have is what we expect. This is going to work, as we have seen. This produces an error. So once we want to start to do operations, some operations will work with numbers or characters, others will only work with numbers. So again, we have here very simple steps, but these principles are those that we're going to use tomorrow when we have bigger data. Do we know what we have? And we need to know that sometimes there are conversions that might happen. We need to be aware as much as we can. So let's go back to PEPs here. So now here we have a vector of length 3. What if I'm only interested in the second peptide? I just want to access peptide number 2, IDG and so on. I can use the square bracket operator. As statisticians start to count at 1. Computer scientists start to count at 0. Yes?
This is a silly question, not silly. How do you clear the console? Like when you go on there, are you clearing?
Thank you for bringing Control L. Yeah, sorry. Control L, and I do it a lot because again, if I start typing here, it might be difficult to see. So square bracket operator 2, okay, will extract my second element. Square bracket operator 1, first one, and so on. There is no 0. Okay, we start to count at 1 here. So what happens if I type this? Anyone? So, what is PEPs? Yes. Vector of characters. Of length? What really matters is that the length is greater than 3. So what is going to happen here? So how can we decompose this to start to understand it? So square bracket operators means subsetting. So how is this subsetting going to happen? We need to see what do we have inside the square brackets operator. What do we do inside the square bracket operator? We concatenate 1 and 3. So we create a vector of numbers of length 2 that contains 1 and 3. So what will be the output of PAPS, square bracket operator C13? Pardon? Peptide 1 and 3, yes. A vector of characters, because that was the input, of length 2. Length 2 because my subsetting here is a vector of numbers, of indices of length 2. And in this case, I get exactly that peptide and that peptide. But then again, exactly which peptides is easy for us to follow on screen because this is small data. Once the data gets big, we need to accept that we don't see it, and we need to trust R to do the subsetting correctly. There are no bugs there. There are bugs in R, but not in subsetting. Too many people have used it for a very long time. Okay, so our job as biologists, data scientists, statisticians, is to make sure that what we type here makes sense. Okay, so it's a kind of a long step, but the science is here. Why peptide 1 and 3? This is just a toy example, but that is the question. How are we going to write this R code that will extract subsets of big data sets that make sense to us? And that could be calculate p-values, select the p-values that are smaller to 0.01 or whatever limit, whatever threshold you want, and then give me the protein names that have a p-value smaller than 0.01. That includes doing a t-test, getting p-values, finding the p-values that are smaller, and then extract relevant proteins. Okay? It's exactly what we do here. We don't have proteins, we have peptides. We could do the test at the peptide level. Let's assume that we have identified that peptide number 1 had a p-value, a small p-value, peptide number 3 had a small p-value, and these are the peptides of interest. What will we get here? A vector of 6 peptides. Now, the first one, the third one, first, second one, doesn't really matter. We are not going to do our job, but that's exactly the kind of gymnastic we need to do. We have an input, a vector of peptides, of characters, we do the subsetting. The output is actually, the result is bigger than what we started with because some of these elements will be repeated. Okay. So let's try to do another type of subsetting. What do I get here? What will be the output of this? Anyone? You need to speak. You need to be louder. I just hear something really vague in the background, so I don't know whether it's the answer to my question. Anyone?
Error.
An error? Ah, okay. Yeah. Well, why? Why not? I mean, sure, many errors we will get them.
Because false might return 0. There's no
Okay.
0
Okay, yeah, that's good thinking. Yeah, absolutely. Somebody else? Another idea? There is no right or wrong answer here. We don't care.
The first and the third one.
So what we have seen so far is subsetting with indices. We can also do the subsetting with logicals. So do I want the first one? Indeed, I do. Do I want the second one? No, I don't. And I want the third one. So I get the first one and the third one, which actually is the same thing as this, but the reasoning behind it is very different. The way we might construct these subsetting operations can be very different. So let me create a slightly bigger vector. See, I don't know, 12, 34, 33, some really big peptides here, and some very small ones. Okay. And so I think now things will start to become a little bit more interesting once we start use comparison operators. Okay. So what happens, do you think, and the do you think is important. The do you think is important because it helps you try to think, how does R work? And at some point you'll feel confident. I think I start to understand this naughty beast, R. And that's when you realize that you'll be wrong. And we need always to, we must expect to be every time wrong with R, because R is sometimes a bit messy. It makes us feel at home. It doesn't get boring with R, as we'll see later with missing values. So what happens if I ask this, for example? Pep length greater than 10. Now this is a difficult question. Anyone? So what do you think will I get as output? What do I have as input? What is this? Yes. Of numbers, what's the length? 10 or whatever. Length. If you don't know, just say the length of this variable is length pep length. That's what R would do. Okay, so the input, this is of length 10, this is of length 1. Okay. So what do you think will be? There could be an error. When it's not an error, very often it's a warning or telling us that something is wrong. It doesn't stop, but it tells us something is a bit weird. So my input of length 10, and then here input of length 1. What do you think would be a reasonable output of this? Is returned, and you say true.
Well,
that's
I
interesting.
that just so I know, but what I initially thought was it would return the numbers.
So I have an input of length 10. These are numbers. My output will be an output of length 10, but these will be logicals. And the first index is true because the first index of input is greater than 10. Second, third, all these are true, and these ones are, that was not on purpose, but the 4 last ones are smaller than 10. So here, and that's exactly my kind of p-value example that I gave at the beginning. It's just these are not p-values, these are peptide length. So let's imagine that I have my data set, and I'm actually not interested in short peptides. I only want peptides that are greater or equals than 6. So I have this input. It's a small input now, of peptides. We know that the kind of quality of identification for short peptides is not great. So what are we going to do? We're going to subset our data, not on p-values, on peptide length. This is how we tell R just to tell us which indices are indeed greater or equal than 6. And now I'm going to repeat what I did before with the subsetting. I don't do the subsetting by index. I do the subsetting using logicals. But my logical vector is calculated automatically. This is the expression that will return true or false whether this condition is met. And then this is recycled automatically to only return my inputs that match this condition. Actually, this is what I want. Okay, great. I had a bug in my software. But if I look at my outputs, I will quickly realize that I had a bug. I didn't need to have smaller than 6, but greater or equal than 6. Yes, thank you.
One step before that, so it says less than equal to 6, but there are 7 values, right? So there are
So here at the top,
Oh, the next step.
this one,
Yeah, greater than equal to 6. Yeah.
here.
It's 6 and 4 false and trues, right?
So my input, which ones are greater or equal than 6? Everything but 1, 2, 3.
But in the output for false and trues, just
Yes, here, this one. Oh, but here I mistyped. I had a bug in my code. Here it said smaller or equal than 6. But I really, and indeed, here if I do my subsetting, I get 6, 3, 2, 1. These are those that are smaller or equal than 6. So it's very easy to write bugs. I wrote this instead of that. But I looked at my data. I do not trust the code blindly, and I fixed it. Okay. So this is data analysis. This is real data analysis in R. So a small data set, but this is the real thing. I'm going to do a little bit less of typing here. I'm going to show the examples. I can combine these operations with an or with an and. So here I'll take all my length and check. Are they either smaller than 8 or strictly bigger than 50? Those that match these two conditions will be true and they will be returned. Here, and in this example, it's 17 and 7. You know, if I ask those that are smaller than 12 and equal to 10, equal with two equal signs, my output is numeric of length 0 because there was no peptide that matched this expression. So we can combine, construct subsetting, and that is a very important part of doing data analysis. So here's another one with the peptides. So I'm not going to type this because that would be too much peptide. So which one of the peptides are either exactly equal to this sequence or exactly equal to that sequence? And there is typically a different syntax for this. Instead of saying exactly equal to one sequence, exactly equal to the other sequence, what we type is perhaps in with a percentage sign. Which peptides in PEPs are included into this other vector that I created on the fly? My first one is not within these. My second one is within these. My third one in PEPs is in this set, and my fourth one is not. And so, for example, if you look at the intersection, you have replicates. You have a set of peptides in replicate 1, a set of peptides in replicate 2. These are the peptides in replicate 1. These are the peptides in replicate 2. Which peptides in replicate 1 are also in replicate 2? This will give you the result. And what we need to do is to familiarize ourselves with this notation. We see that we open a square bracket operator, we close it here. And then there is the in. So here's a vector, and here's the other vector. It's a function that starts here, because here I open my parentheses, I close it here. So kind of splitting these just like cat. And then my children put them together and make cat out of it. We need to do the same thing. Oh, in, here's a bit, here's a bit. Function starts here, ends here, and so on. There is a very important value in R that was already discussed during Olga's lecture, which are missing values. Okay? And in R, they are called NA. So I'm going to use a bad variable name here, X. And it's bad because X is very generic. Very often we will want to have slightly more informative variable names, but not too long because that means more typing. But when we demonstrate, when we just try things, X, Y, Z, A, B, C. Oh, actually. X, Y, Z, yes. A, B, better not to use C. Why do you think it's not a good idea to use C as a variable name? Because there is a function called C, yes. Now, R is clever enough to realize that if we have a variable C and a function C, it will know whether we mean the variable or the function because of the parentheses. But still, it's a good practice to avoid naming two different things with the same name. So, NA. If I look at the class of X, it's a numeric. Okay? So the NA is there, but the NA is still a number. Actually, in R, we have different types of missing values. We have missing numbers, we have missing characters, and things like that. But there it is. It's still a number, and one of these numbers are missing. It's not 0. That, if I said, oh, I don't know, I'll just put 0, that is making a very strong assumption. That is doing your protein quantitation imputation, just putting a 0. And this might be a very bad choice, depending. Okay. But NAs, and we will see that we have this, exactly that kind of example as I'm going to illustrate now. Let's try to calculate the mean. Okay. The mean of X. What? Any suggestions? Somebody wants to dare to predict what R is going to do? Error. You would like an error. I think it's a very valid suggestion. The only problem is that if that would produce an error, we would get many errors in our scripts. In proteomics in particular, if we do label free, many missing values, too many errors. We get enough errors, just by mistyping things. So, no, it won't be an error. Yes? Okay. Anyone else? We get an A. Because it's not defined. There is 1, 2, and then something that we don't know about, and then 4. And R is not going to take any risks. It says, I don't know. It's a missing value. So, how could we get around this? And there are multiple very good answers. How could we get around this?
Maybe convert, maybe convert not an A to 0. I'm not sure that that's correct.
I don't like it. Don't do that. No?
Convert any to strings and then specify which ones are true, which ones are false, and then get around.
So we could type X, C, true. Oops. Oh, actually, true. We could type true, true, false, true. I could type 1, 2, 4. Yeah. What I could also do is .na X. Which ones in X, which elements are NA, are missing? It returns false, false, true, false. So another logical operator is not. Which ones are not NA? True, true, false, true. So that's one way to kind of create this vector of logicals that tells us which ones are NA and which ones are not. And now I can use this to subset X. And now I can use this to calculate the mean of this vector. Okay. So let me put this at the very top here.
But you can't just type mean X. Unless you add that in.
Mean X is NA.
So you have to tell it to exclude false or return just.
Yes, exactly. If we want to calculate the mean, so the mean of a vector of numerics, whatever its length, if there is a single missing value, the mean of that vector will be missing value. Okay, so here is one way to do it. And I would like to appreciate this line of code. It is not very long, but it is not straightforward to parse it mentally. many things happen there. You know, we have a function with parentheses, and then a variable with square bracket operators, and then another function with another set of parentheses. Okay? So actually, if I had started the session with this, many more people would have left. You know, because this is not trivial to read. But I hope that maybe you can't read it straight away when you see it, but you got the tools to start to parse this. And understand that even if by just looking at it, it doesn't immediately make sense, you start to understand what these succession of cryptic symbols mean. Yes? Yes, so it has to be capital and capital A. Yeah.
So can you elaborate on the function each.na?
Yes. So X is my first element of X and A. Is it? Is the first element of X and A? Is it missing? No. Is my second element of X missing? No. Is the third element of X? Fourth one? Oops. Is dot NA not as environment? That is exactly what is an A does. Now what we want is not to know which ones are an A. We want to know which ones are not an A. For that, we use exclamation mark, which is the negation. You know, the opposite of false is true, the opposite of true is false. So by getting the opposite of is an A, we get those that are not an A. We use this to subset. Subsetting is with square bracket operator. To subset X, only get those that are not an A, and we put this as input to the function mean. This is not trivial. And just by looking, just by looking at it, it is difficult. But we did not write this in one go. You know, that would be lying to you if I just said, oh yeah, I know R. That is not how it works. Even, and I have many, many years of experience, you do not type that in one go. The way you construct these expressions, and much longer, much more difficult expressions, is exactly when you do that. X, oh, there isn't an A. I don't, which ones are an A? I want the opposite. And now I use this. I didn't start typing me. Let me show you how I typed it, even if it's in one line. This is how I typed it. Is an A X. I go at the very beginning, not. I want to use this to do the subsetting. Subsetting is the square bracket operator. I want to subset X, and this I want to use as input to mean. This is how I typed it. So the way I typed it is the way I reason on my data. Good. But actually, we are all wrong because we didn't read the bloody documentation. Question mark mean. Here we go. The mean, what kind of inputs does it take? X, trim, if you want to trim it, and a.rm equals false. So instead of working with our brains, which was a good exercise, we would have read the documentation. We would see that it is enough to type X and a.rm equals true. So here we did all the work manually, but because this happens many, many times when we do data analysis, there is a shortcut. And the shortcut is to tell the mean function, yes, we want to calculate the mean of this input. But if there are any missing values, first remove them. RM is to delete, remove. So it helps to read the documentation. And actually, there is a last way of doing it. It's to use an a.omit. An a.omit X returns X where all the missing values have been dropped. It comes with a little bit of annotation, but we can just ignore this. So a little exercise here for you. Please type in this vector of length. Create a new variable, call it length 2 or whatever you want. Create a new variable that contains this data without the missing values. And once you have done that, try to call median. We have done mean, but call median of this length vector and this other vector that you will have created without the missing values.
What was the omit function?
And a.omit. So I'm going to here, and a.omit. And here's the question. And when you have finished the exercise, please use your green sticky notes. If there is a question, please call us or use a red sticky note. Olga? We have until 6 or 5:30. 6? Can we proceed? My right-hand side is much better in terms of green sticky notes. I don't think it's because they are better. I think they just like sticky notes and you don't like them that much, which is perfectly fine. We don't discriminate on sticky notes. Before we look at we don't discriminate on other. I'm European, sorry. So here on the left-hand side, I copied the kind of creation of this vector. And I added a new line here, after the 18 comma. So let me execute this very first line here, Control Enter. Now, RStudio is too clever, so I'm just going to copy and paste it, okay? And press Enter. Do you see that here I have a little plus? Okay? I do not have a greater than sign, which means R is waiting for me. I have a little plus, which means R is waiting for me, but is waiting for me not doing nothing, but waiting for me being ready because it knows that I haven't finished typing. How does it know that I haven't finished typing yet? Yes, I have opened a parenthesis, but I have not closed it. So I can keep on typing. I'm going to type the same thing, 20, Enter. Now it sees that the parenthesis is closed, so it knows it has finished, and it reverts to I'm waiting, but just because there is nothing to do. Okay. So that means that here I can format these the way I want. I could write 2 values, comma, 2 values. I could write like that. I could write it in one line. This doesn't matter. The general advice is avoid to have really, really long lines because they are more difficult to read. I always put a space after my comma. I could also have something like that. I could write it like this. It is valid R code. It just makes my eye bleed because I don't like it. I always want a comma, a space after a comma. Because I think that R code is easier to read when lines are not too long, and not too long is universally accepted as being 80 characters. Some people say 70, but 80 is universally accepted. Or the majority of competent people say 80 is too long. I'm joking. You choose whatever you're, if you want to write really, really long lines, that's fine, but they are often more difficult to parse mentally. Spaces, again, don't matter. We could even have a space between the function name and the opening parenthesis, but this is very ugly. Please don't do that. Or don't show it to me. I find it absolutely horrible. There are several kind of syntax guides, and nobody says this is a good idea. Okay. However, it would be an error to put a space here. Why is that? And actually, look, using RStudio is great because this editor is really clever. It identifies that there is a problem on this line. So even if I'm not really good at typing, but I use the editor, the RStudio editor will help me to identify bugs. And why putting a space in there is a problem? Not the fact.
We haven't defined it.
What have we not defined?
Something that's written as alien space.
So we are not allowed to use spaces in variable names. This looks like variable len, space, and then we assign this vector to another variable gths. But this is not correct. This would be 2 expressions, one that has only the name of a variable, the second one that assigns a value. We are not allowed to have 2 expressions in one line in R. What we could have is this. This would make it a valid syntax. My first expression is len, which would be, is there a variable len? If yes, return its content. If not, return error. And then something else, which is assign 1024, and so on, to a variable gths. But this is not correct. So we are not allowed to have spaces in variable names. Otherwise, there is a bit of flexibility. All right, so we have missing values. How could we get rid of the missing values? A bit down. na.omit, yes. How was it called? Length. So if we want to call the median of length, what do we get? If we call the median of this, oops, not mean, median, we get the median value. But actually, is there there is an na.rm in median. And actually, many of these functions will have an na.rm. Because the default behavior in R is, if there is a missing value, I do not take any risks. I just say, I cannot compute the result. I just want to get back to one thing that I kind of glossed over, which was this, greater than 10. Actually, what happens here is a very important rule in R, which is the recycling rule. On the left-hand side of my operator, I have a vector of 10. On the right-hand side, I have a vector of 1. So what R does automatically is to repeat the smaller vector enough times so that its length matches the longer vector. Let me illustrate this with another example. If I say C1, 2, 3, 4 plus C1, 2. Keeping in mind the recycling rule, what will be the result of this? Anyone? Doesn't matter if you get it wrong. No, let me. 2, 4. Let me just create two variables, x and y, C1, 2, and print them like this. So length of x is 4, length of y is 2. Y is shorter, so R is going to recycle. So what R is really going to do is going to sum x and is going to sum y. Okay. It's going to sum each element of x and each element of y repeated twice so that the length of y matches the length of x. 1 plus 1, 2 plus 2, 3 plus 1, 4 plus 2. So recycling rule is a very, very important rule in R that applies to numbers, to characters, to logicals. It will always recycle the shorter one. I was expecting that question. Let's try. So let's say y is 1, 2, 3. X, y, x plus y. Anyone wants to have a guess? An error? Well, I wish it was an error. And the warning message telling me that, there is a longer and a shorter one, but, I can't get an exact match if I multiply the shorter one. Okay? So whenever you get warnings, you might get results somehow, but this indicates that probably some of your assumptions were not correct. Doing x plus y when x has length 4 and y has length 2, maybe that is what we want to do, and we want it to, recycle. Maybe here, this is not what we wanted to do, and R points that out with a warning, but it still does the calculation. The last thing that I skipped over is installing packages. Installing packages is done with a function. The function is install.packages. So I need to know the package I want to install. For example, ggplot2, which should already be installed on the computers. So install.packages is going to automatically look up in a central repository of packages for this ggplot2 package. And it's going to download ggplot2, but it's also going to download all its dependencies. This central repository is called CRAN, Comprehensive Archive Network, I think, don't remember. So although I asked to install ggplot2, it's going to install all the dependencies, automatically download them, and finally install that package. What I have done is only installing it on my computer. If I want to start to make use of it, I first need to load it. And this is done with another function called library. This now loads the package ggplot2. So now I can use this extra functionality after first installing it and then loading it. just to look again at session info. Do you remember session info? What does it do? Yeah, it got general information about my R session I'm running right now. And actually, now here in this section, I see ggplot2. I must see here. Okay. So the first time I ran session info, or if you run session info without loading ggplot2, you will not have this. Okay. So a session info also tells me and people that might answer my question, all the packages that have been loaded. Install the packages, and then loading the library. It's slightly different for bioconductor packages. Actually, bioconductor is a kind of a project that focuses on the analysis of high throughput biology data, genomics, proteomics, metabolomics, flow cytometry. It has been created by one of the two original authors of R. So the original authors were Rossi Harker and Robert Gentleman. And Robert, after starting R, created the bioconductor project that specifically defines packages for the analysis of high throughput biology. So we're not going to talk about bioconductor here, but if you are going to analyze proteomics data or any high throughput biology data, if you do any genomics, microarrays, or high throughput sequencing, chances are that you have used, or your colleagues have used bioconductor. Okay. Any questions about? Yes. Sorry. Once they are installed, they are written on your hard drive. So if I close R now, let's do it. No. Let's just do it. So if I quit RStudio, and here's one thing. So if I quit RStudio, it asks me whether I want to save everything that I currently have in my workspace. I haven't defined workspace. There are a couple of concepts in R that define location. One is we created this R project. By creating this R project, if R is looking for files or R is writing files, it will always start looking at these files inside this project directory that we created. So that is called the working directory. That's the kind of the starting location on your hard drive. That's called your working directory. And then there is your kind of workspace or global environment. That is kind of the home, if you want, where all the variables are stored inside R. And here, in your global environment, in this panel, you have a kind of an overview of all variables that were created. Okay? That's the kind of the home location inside R. Your working directory or your R project directory is your home directory on your hard drive. Okay? So there are two concepts of where is R going to look for things. In R is your global environment or your workspace. On your hard drive is your working directory. So if we use RStudio, I'm on a tangent here. I'm going to answer your question. If I install a package, it's installed. I can close R, open R again, or RStudio. The package is still installed, but I will have to load it again with library and the name of the package. It overwrites it. So if you install the same version, it's fine. If in 6 months we reinstall ggplot2, it's most likely we'll update the package and install the new version. Quickly, another function is the function ls. ls lists all the variables that are in my workspace. Now, if we use RStudio, we see them here. But this is another way to list all the variables, all the variable names. I can remove some variables with rm. rmx removes variable x. If I list my content again, I had weight x, y. Now I have weight and y because I have removed. So when I close R, do I have a quit here? R or RStudio here asks me whether I want to save all the variables that I created in a default file called .rdata in my working directory. So it will, whatever I created, whether it's something important or just temporary variables, it will store everything in this one file. I personally never do that. I never do it because when I start R again, in that directory, it will reload all the variables that were created. Many variables are just created kind of as temporary variables. If there is anything important, I will want to store the code that creates these variables in an R file. And so if I close R and open it again, and I want to regenerate these, I rerun this script, and it will execute all the lines and regenerate all the important variables, and not the junk variables that I don't want, that just kind of are there in my environment because I try things. But if you want, you can store everything. Next time you open R, it will load everything. If you have big variables, R will take some time to load everything. But storing everything and loading everything is not a way to have reproducible research, because you don't know how these variables were created. If you want to know what happened in the past, you need to write it in an R script. But there is actually a second way to implement reproducible research, and it's by using a very kind of a plain markup language called Markdown. Who has heard of Markdown? Markdown is, if you want to write HTML, it's a bit complex. You have these special characters if you want something in bold, heading, level 1, level 2. If you use LaTeX, it's even more convoluted. It's very beautiful, it's more convoluted. So Markdown is a plain text way to write text with very simple markup, bold, italic, things like that. An extension of this is called R Markdown, and that's extremely powerful because it allows you to mix text, prose, description, and R code. And RStudio has made the creation of these R Markdown documents, or sometimes called vignettes, very, very easy. So let's create such an R Markdown document. File, new file, and here I choose R Markdown. So earlier today we created a new R script, which is a simple file. Actually, I didn't specify. Here it is. An R script is a text file. No, wrong button. Is a text file that has extension .r. Capital R or lowercase r, it doesn't matter. It could be an S, lowercase s or uppercase S. And the reason is that before R existed, there was another piece of software called S. And if you read the very technical documentation that you don't understand, they even say that, I think it's Q, I never got YQ. And that would be horribly confusing. So whenever you have an R code, it comes in, or an R script, it would have the expected extension is .r, capital R or lowercase r. So this R script is something we created at the beginning of the session. File, new, and this time we're not going to create an R script, but an R Markdown file. A title, I love R. I think I can confidently say now that we all love R. And an author. And I'm going to keep it to HTML now. OK. And so here it is. This is my R Markdown file. So this is a little bit of metadata. So I provide the title, an author. It automatically produces a date. If I don't want the date, I can remove it. And here it says the output is going to be HTML. It could be something else. We'll see that in a second. This is not terribly important if we use RStudio. And then what we have here is Markdown. So the Markdown syntax starts with two hash tags. If I want to have a section of level 2. If I wanted to have a section of level 1, I would have something like this. Section 1. Okay. And this implicitly is a section 2. Okay. Now, it doesn't really look like a section 1. It's not bold. It's not bigger, like you would have in Word. But this implicitly means this is going to be a section 1, this is going to be a section 2. And it will be rendered in a nice way later on. And so here we have a little bit of text. Here we have another way to kind of highlight the font with 2 stars. This means it's bold. 1 star means it's italic. So we don't see it here, it's text. There's a little bit of colors to help us see it. But what is really, really great is that within this document, I also have chunks of R code. So what this line of code does is that it takes an input, which is pressure. It's a data set that comes with R, and it plots it. We're going to see plotting in detail tomorrow. So what I would like you to appreciate is in this text here, in this file, we mix and match plain text and R code. Here it is, another chunk of R code. And so if we press the magic button, if we want to knit the document. So what knitting a document, I'm first going to show you. I'm just going to click the magic button here. I'm going to save it as test 1, where it automatically suggests to store it in my R project directory. And here's what happens. I love R is my title. Here's the author. Here's my section 1 with 1 hashtag. Here's my section 2 with 2 hashtags. Here's a little bit of code. Knit was in bold. Click was in italic. Here is this piece of R code. We're going to see summary in detail tomorrow. Cars is like a spreadsheet with information about cars. Well, this is the piece of R code that we had as input, and this is the output of running this piece of R code. But we never run it. We never copy and paste the output. Knitting means take this R markdown file, extract the R code, execute it, and take the output of this R code and put it back inside the markdown file. A little bit more text here, and here is a figure. This is the output of time plot pressure. You should not believe me. How can I close this? This is where it becomes clear that I'm not a Mac user. I'm just going to close it. Here. Plot pressure. Let's type plot pressure. And it automatically creates this graphic in this panel here. So when I produce this figure interactively, it opens it here. If I want to create this figure in an R markdown file, it produces the figure and inserts it into my document. Knit it again. So this is another way. So I had a question, how to take notes. One way was to use an R script and write R code and then add a few comments with the hashtag. Another way, a much more powerful way, would be to create R markdown documents. So throughout the this module and next week, if you are here, whenever you do R, my advice would be create an R markdown document. for the first day of the intro, the second day of the intro, the third day of the intro, create these R Markdown documents that include code and include text. And then you click on the button, and it will automatically execute all the code and replace it and add the output. That is extremely, extremely powerful. Imagine that I write this R Markdown file that takes a spreadsheet, that takes the output of your favorite quantitation software, Skyline. Okay. Skyline produces a text file, a CSV file. Imagine that you have a script that reproduces the analysis in the RPG dataset, the paper, this study that Olga created. Okay. Imagine that you do this analysis, a good analysis that you trust, you told to your colleagues, with your bioinformaticians, statisticians in your department. You come up with a really good way to analyze the data. And you prepare an R Markdown file. The first line of code of that R Markdown file reads the input of Skyline with a piece of software that knows how to parse it. And then in all subsequent sections, you produce plots, quality control plots. And then you have a section that does the statistical analysis, as we're going to see on the third day, and so on. And then you click on the button, and that automatically generates a report in HTML, as we have here, or if you prefer, in PDF. In that case, you would go here, knit to PDF. Same thing, it knits the document for you. And now, the same input, R Markdown, is now used to generate a PDF. And if this was the analysis of a proteomics data set, you could generate these reports for any input, any standardized input. As long as the Skyline doesn't change the way it exports its data, you could just change the file name at the very beginning and create these reports that do your QC, your analysis, as long as the experimental design is the same, systematically for all your input files. So this is an extremely powerful tool, R code and Markdown, to produce these reports. I don't know if you realize how powerful it is. I don't know. Do you see how excited I am about these R Markdown files? It is extremely powerful. So we have 13 or 12 and a half more minutes until the official end. So my suggestion is enjoy R Markdown. Just try it out for yourself. File, new file, R Markdown. It will ask you a title and author, and then click on the button, the magic button, to create an HTML file and a PDF file. And then just think about all the possibilities, with R Markdown. Okay? Just have a go. Play with R Markdown. Orange sticky notes if there is a problem. Green sticky note if you like it. And then we'll just wrap up in 5-10 minutes.